Okay, so key points for today, we need to understand what information can be read, okay, from kinematics graphs, again specifically position versus time and velocity versus time graphs. And we got to look at how graphs and equations from kinematics show the same information in different ways. In fact, many, if not all, of the equations that we use in this unit are actually derived from those two graphs. Okay, from either a position versus time or a velocity versus time graph. Right, so we'll be looking at where those come from as well. All right, so we got position versus time graph. As the name would imply, the two things that appear on that graph are position and time. So you can read from that graph where an object is at various points in time. That is all you can read directly. You can, however, infer or deduce a number of things based on the shape of the graph. And you can also calculate total displacement, total distance, average speed, and average velocity. The same things we were looking at last week in formula form. Now we're going to look at them in graphical form. Okay, so it'll be very similar mathematically, but the questions will set up a bit differently because they'll involve a graph instead. Questions so far? All right, so don't be afraid to ask it. There are some that come up. Okay, the first part of the graph that we see here, this position versus time graph, so from this dot back, this is just a straight diagonal line, right? And it says here that at this point, it is traveling at a uniform velocity of 180 kilometers per hour. So why does a diagonal line on this graph indicate that it's traveling at a constant velocity? This is something we would have gone over in Science 10. So I've got a position versus time graph. Okay, and I have just a diagonal line like this. The position is changing, and over time, and even more importantly, it's changing at a constant rate. Exactly. Right? That means. Okay, that means that the amount the position changes by every second is exactly the same. Right? So if we say this thing is traveling at 180 kilometers per hour, that means every hour it will be 180 kilometers from the last point that it was recorded at. Okay? And that would happen continuously, which is why we get a diagonal line. Is that all right with everybody? Okay. After that dot, we see that the line is curved. It's curved and it's flattening. Okay? So it's getting flatter and flatter and flatter. So if I look at, let's say, this graph here, so this is a straight diagonal line, so is this. I know they don't look it because I keep, for some reason, kind of bending at the end, but they're straight. Okay? So these three lines, A, B, and C, which one's the slowest? C. Okay? It's the slowest because it's the least steep, or in other words, has the lowest slope. Everybody all right with that? I mean, you kind of have like a feel for that. When you look at a graph, anything that's steep is high, anything that's not steep is low. Okay? So C would be the slowest one. Well, when we have a curve that's getting flatter and flatter and flatter, it's because it's going slower and slower and slower. Okay? It's changing its velocity, right, in a way that makes the line less and less steep. If it was constant, it would be a diagonal line. But because it's slowing down, the slope of that line is slowly getting flatter and flatter. Okay? Everyone with me on that so far? Okay, so anytime we see a curve, any kind of curve, whether it's an ascending curve or a descending or flattening curve, okay, we are looking at a decelerating object, okay, or a slowing object. We generally don't use the term decelerate in physics very much. We just use the term accelerate. Okay, accelerate means any change in velocity. Right? It's a negative acceleration if it's slowing. It's a positive acceleration if it's speeding up. Questions there? So here's where that idea comes from. I'm going to explain to you the only thing I understood in university calculus. It was the first day. Every day after that was a struggle. Okay? I got through it by memorizing the examples in the textbook and writing them down on my final exam and getting part marks for method. Okay? I don't recommend that as a method of success, but I was good at memorizing and not good at calculus apparently. Okay? So, when a mathematician sees a curved line like this, or the flattening line that we saw in the other graph, what they see is what you or I would see if we were looking at a low resolution picture or video on the internet. Okay? They see, what do you see when you see a low resolution picture? You see the pixels, right? You see the little squares. Okay? Because a computer can't make a curve. It can make little tiny straight edges or little tiny squares. If they're small enough, we can't resolve them with our eyes, and we call that high definition or ultra high definition because the pixels are so small we can't see them. Okay? We're watching something in like 480, then it looks like a bunch of boxes moving around randomly. Okay? But when a mathematician looks at this curve, what they really see is this line, and then this line, and then this line, and then this line. Okay? They see these tiny little lines that are getting steeper and steeper. Each one of those lines obviously has a slightly different slope. And on this graph, slope corresponds to velocity. So when we have a curve, okay, what we see is an ever steepening kind of best fit. Are you all right with that idea? Okay. So for this part here, what we're seeing is a line that's getting flatter and flatter and flatter until the slope is 0. Yeah. When it's flat, the slope is 0, right? It's not going up, it's just going over. Okay, how do I know that between here and here, the object is stopped, besides the fact that it says it's stopped on the graph?
It's at 0 over a course of time.
Exactly. It's at 0, and its position does not change for 0.2 hours. Okay? So it's stopped there. Then we see in this part of the graph that now we have a steepening line. Well, that's accelerating positively. It means it's going faster and faster. The line's getting steeper and steeper. And then here at the end, we have another diagonal line, except it looks way better than what I drew. Okay? And that means traveling at a constant velocity of now 200 kilometers per hour. All right. Which of these two lines, this one or this one, is steeper? Exactly. Remember, slope corresponds to velocity. The steeper the line, the higher the velocity, or the faster they're going. So if that one's 200 kilometers per hour, it's going to be slightly steeper than this one. It's hard to tell that kind of on the graph because there's not any grid lines or anything for reference, but that one would have a greater slope because slope corresponds to velocity. Okay. Now, on this graph, you've probably seen this formula somewhere. Agreed? Maybe it was written like this. Okay. We don't like that formula very much in physics because it's kind of useless other than calculating slope. Okay? It's true, it's perfectly valid, but it only really has one good use, and that is to calculate the slope. Okay? We in physics typically want to be able to calculate other things other than slope from a graph, so we use y equals mx plus p. How many people have used that formula before? Okay, we're going to go over how it works with the graphing for a linear function, okay, but we'll use it. Okay? What I want to show with this formula right now is why slope on this graph represents velocity. Okay? On this graph, on the y-axis is position. On the x-axis is time. You're all right with that? So really what we're seeing here is that slope equals final position, my second y value, minus initial position, my first y value, divided by my final time minus my initial time. What does final position minus initial position calculate? we used it last week. This thing, this word, is your change in position. Displacement. And final time minus initial time, very simply, calculates time. Total displacement divided by total time equals velocity. Okay? That's why the slope of that graph represents your velocity. Okay? Now I know in Science 10 you probably just memorized, because you only had 2 graphs you were going to work with, you just memorized that the slope of this graph is velocity, the slope of this graph is acceleration, and this is how I calculate displacement. But we don't want you to memorize everything in physics. Okay? I mean, I kind of walked through this process slowly, but in the end it didn't take very long or very much thinking to figure out what the slope of this graph represented. Okay? By the time you're done Physics 30, you'll have like almost 50 different graphs that you use. Memorizing what the slope of every one of those 50 graphs represents is going to be a lot more challenging than just learning how to figure out what the slope of a graph represents. Okay? If we can remember how to figure it out, that's far more useful than trying to memorize 50 different graphs and then getting them confused. Okay? So what we want you to do is kind of go through this process when you encounter a new graph. Ask you to calculate something, look at it and go, okay, well, would the slope represent that? Set it up like this, figure it out. Okay? Same would be true for a velocity versus time graph, and we'll go over that when we get to those. Okay? So, right now, is everybody okay with this? Okay. Alright, so that's what we were just looking at a minute ago. Okay, we said slope equals, final position minus initial position over time. B equals d over t. Okay, but we also want to be able to use this. Okay, y equals m times x plus b. Okay, this formula calculates a lot more than just the slope. What part of this equation is the slope? M. M is the slope on here. Okay, x is the x value of a certain point, y is the y value, corresponding y value of that same point. What's b? The y-intercept. All right, so if we're kind of labeling these things on this graph here, right, we'd be looking at this here would be b, right? This up here, okay, would be y. This would be x, right? And then the slope of the line would be m. Now, we just looked at this formula here a second ago, right? But if we manipulate y equals m times x plus b to get the slope, are we looking at essentially the same thing? Right? This is my final position, y. This is my initial position, because it's where the object was at time 0, and x is the total time elapsed during that time. Okay? Everybody okay with that? Just ringing a bell a little bit from Science 10? All right. So one of the challenges that you're going to have is being able to interpret a graph. Okay, that is to look at a graph and maybe I ask you, what is the object doing in part D? It stopped. Okay. How do I know this object has stopped? Because it's flat. Its position doesn't change at all between, what are we looking at here, 9 seconds and 12 seconds, or 10 and 12 seconds, maybe I'm not trying very straight. Okay, but during this section here, okay, its position doesn't change, so it's stopped. During which parts of this graph is the object moving backwards? Okay, not all of C. Part of C, it's moving backwards, but not all of it. Where else on this graph is the object moving backwards? E and F. Okay, Okay, now this throws people because they see lines that are going up, and up indicates positive in our mind. Except, where is the object? Okay, the object is down here in the negatives, right? It's behind where it was before. Okay, so, sorry, I said that wrong. I had a velocity time graph in my head. Forget everything I just said for the last 15 seconds, because I was looking at this like a velocity time graph. See, that happens sometimes. You were right. In part C, the object is moving backwards. I had this totally velocity. I'm getting ahead of myself. Velocity versus time graph in my head. Okay, how do I know this object is moving backwards here? What's the position of the object doing during part C? Decreasing, right? So it starts part C at a position of 6 meters, but by the time section C is done, it's at a position of negative 10 meters. The only way to go from positive 6 to negative 10 is to go backwards. Okay, but during parts E and F, which I just told you were the other way, okay, it's actually moving positively. If this was a velocity versus time graph, these would be moving backwards because they're negative values, which is what I had in my head, but they're not. Okay, so this is a position versus time graph. So in these two parts of the graph, because the position is becoming more positive in these two parts of the graph, the object is moving forwards. So what this object is doing over the course of the entire trip is going forwards, and then what's it doing in part B? Stopping. Part C, we already said, moving backwards. Part D, we already said, stopped. E and F, right, retracing back. All right, here's another thing you might be asked on this graph. What is the total displacement of this object over the entire trip? 0. How do we know that? Exactly. Its starting position and its ending position are the same place. It starts at position 0, ends at position 0. Came back to where it started. So the total displacement is 0. All right. What's the average velocity over the whole trip? Ooh, I was expecting a quicker answer on that one. 0. Exactly. If the displacement is 0 and velocity is displacement over time, velocity also has to be 0. Okay with that idea? All right. Is there any point on this graph where the object's accelerating? Nope. Because there's no what on this graph? Right, there's no curves. There's no curves anywhere on this graph. Okay? The object is either stopped or moving at a constant velocity, which is a physical impossibility. You have to accelerate if you're going to have a velocity, but this graph doesn't show that. Okay? All right. Let's see how much you remember from last year. I want you to calculate two things for me from this graph. Total distance traveled and average speed. Spoiler alert, they're not 0. Okay? Because we already did that part. I want you to calculate the total distance traveled and the average speed over the whole trip, assuming the trip takes 18 seconds. Okay, give you a minute on that. Okay, what's our total distance traveled? 32 meters. Okay, here's how we calculate that. Remember that distance is a scalar quantity. Doesn't care whether we go forwards and backwards, just how far do we go in total. So what I need to figure out is how far do I go in each section of this graph, and then I just add all those numbers together because it doesn't matter whether they were forwards or backwards. All right, so in part A I go from 0 to 6. So I go 6 meters during part A. I don't go anywhere in part B. The line's flat, right? Then I go from 6 to negative 10, so that's 16 meters. Then I don't go anywhere. And then I go from negative 10 all the way back here to 0, so that's another 10 meters. Okay, I could do that section by section, but in the end, they're both going the same direction as we already established / Coderre screwed up earlier. All right, so I got 6 plus 16 is 22 plus 10 is 32 meters. All right, there's my total distance traveled, 32 meters. So what's my average speed?
1.88 meters per second.
Sounds about right. Okay, so V equals D over T. Total distance was 32 meters, okay? Total time was 18 seconds. Yeah, that should be about 1.8, 1.9 actually, I think, right? 1.88?
Yeah.
Yeah, 1.9 meters per second. No vector on that because speed is scalar. All right? Those are all things I could very easily ask you on a quiz or a test to do with a position versus time. Okay? That's interpreting a graph, that's some calculations from a graph, okay? That kind of stuff. Okay. Any questions there before I move on? Right. Want to illustrate graphically why we do this thing here, where average velocity, okay, is total distance over total time. Okay, we were talking about that the other day when you have a trip that consists of more than one part, why you don't just calculate the two velocities, add them together and divide by 2. Okay, in this case, we want to take the total displacement divided by the total time. Okay, and the reason for that is because if you have a trip like this one, okay, where you travel at one speed for a lot longer than you travel at the other, you need to weight the average in favor of the part of the trip that takes the longest, or that represents the biggest part of the trip. The example I gave you was if you were driving to Edmonton and you were able to go 120 kilometers an hour all the way to like Leduc or the airport, okay, but then after that you had to go slower, you wouldn't add your two velocities together and divide by 2, because the part that was from here to Leduc is a way bigger part of the trip, okay, than that last little bit. Unless, of course, that last little bit ended up taking you longer than the first part. Okay, so let's say we're going to Leduc, and we get to Leduc and there's a tractor trailer sideways across the road and we're stopped for an hour and a half. Well, now that part might represent a bigger part of the whole. Okay, being stopped for an hour and a half is severely going to cripple your average velocity. Okay, regardless of how fast you were able to go before, you got a lot of goose eggs to put into that. Okay, after that. Does that sort of make sense to everybody? Okay. If I have a graph that has a bunch of curves on it, a position versus time graph that has a bunch of curves on it, what's the object do? It's accelerating. Okay. During which part of this graph is the acceleration positive? That means the velocity is getting bigger. Part A, yeah. Okay, because the curve is going up. The slope of the line is getting steeper and steeper and steeper. Okay. Now, at kind of this point right here, that stops. That acceleration where the speed is getting greater stops. And now we see that the line is getting flatter, right? Okay. In fact, if we're looking at this, and just move this line out of the, move that line out of the way. Okay, when we get to here, right, it actually turns around, starts coming back the other way, right? The position is still increasing, but it's going slower and slower and slower. And then it does exactly the same thing, but in the opposite direction. Okay, and its velocity is getting higher and higher and higher until about maybe, say about here, and then it actually starts to get slower again. All right. Won't this be a graph up? I would never ask you that on a test, by the way. It's not really a fair question. That's a graph of somebody throwing something up in the air and catching it. Okay? During this part, part A, that's when I slowly accelerated the marker in an upwards direction. Okay, I made it go faster and faster and faster. When it left my hand, what started happening to its velocity? It accelerated down, which means it got slower and slower and slower until it got to its maximum height, where for an instant it was stationary. Yeah, for an instant it was stopped. okay? And then it accelerated back down at exactly the same rate, right? So as soon as something is being affected by gravity, its acceleration is 9.81 meters per second squared down. And that's what we see here. This part of the graph is a mirror image of itself. The acceleration is the same, okay? All that changes is which direction the object's actually moving. It's accelerating downwards the whole time, but it's moving downwards in the second half of the time, right? This right here is the start of me catching it, slowing it to a stop. Okay, again, I would never ask you something like that on the test, but I might still ask you to interpret this graph. All right. How do I know that at the top of the flight, okay, there at its highest point, for an instant it stopped? How do I know that?
The force acting on upward equal to the force of gravity coming down.
Actually, no. There's no force upwards once it leaves my hand, right? 'Cause-
Because of the speed.
but yeah, the speed of it, yeah. So it's slowing down, slowing down, slowing down, stop. Speeding up, speeding up, speeding up. The acceleration is the same in both directions, just direction of travel is different, okay? But here's how I can prove that at the top, it stopped. Slope on this graph represents velocity, yes? So if I have a horizontal line, the slope is 0 and it's stopped, yes? There's the slope of the line at the top of that curve. Remember we said a curve is an infinitely large number of infinitely small straight lines all strung together? Well, at the top of that curve is a little horizontal line. For an instant, that object stops, okay? And so its slope of its graph would be 0 there at the top of that little curve. And then it starts going down the other way. All right. You're never going to be asked to draw tangent lines on a graph or anything like that, okay? But it's kind of important to be able to recognize that, yeah, if I do draw a line on here that touches a curve, it represents the slope at that point, okay? Here, the slope is 0, right? But down here, I want this thing. Just let me have this. Fine, it'll be that way. All right, so this line here, I don't want it. Okay, this line here that I just drew would have the same slope as the curve right here at point A. So if I calculated the slope of that line, I'd know how fast the object was going at point A. Right? Because during that whole curve, the speed is constantly changing. Right? You're never going to be asked to do that, but it's just kind of important to recognize that that could be true. All right. I want you guys to try this question right here. Okay? It's a graphing question, position versus time graph. Okay? We've got time in hours and position in kilometers. Okay? So we've got a bus making a trip that's shown on that graph. Okay? I want you to calculate the average velocity of the bus during A, B, and C. So this would be A, B, and C, as well as over the entire trip. Right? I'm going to make that graph a little bigger so you can see it better. Right, so I'll give you a couple minutes on that. I want A, B, and C and over the entire trip. Okay, so average velocity during part A, part B, part C, and over the entire trip. And we'll go through that together here in a couple of minutes. All right, let's have a look at this. So we said earlier today that average velocity equals total displacement divided by total time, which we could calculate by doing this. Final position minus initial position over final time minus initial time. Which we also said was equal to the slope of the line, yes? Okay, so for each section of the graph, will that apply? It certainly will. All I have to do is get the numbers to plug into that formula. So for part A here, when I calculate that, so if I go the average velocity in part A, I'm gonna take my final position, which is 25 meters, positive 25 meters, subtract my initial position, which is 0, and that takes place over 1 hour. So like 1 minus 0, so it's 25 over 1, and I get positive 25 kilometers per hour. Are you okay with what I did for part A? I'm going to do exactly the same thing for part B. Okay, so in part B, my initial position is 25 kilometers. Okay, my final position is like 33, looks like. Okay. And that takes 1 1/4 hours, right? It goes from 1 to 2 1/4. Okay, so 2.25 minus 1. So I'm going to have 8 divided by 1.25, which should give me positive 6.4, okay, meters per second, or sorry, kilometers per hour. And I do the same thing for part C, right? The average velocity in part C will be something minus 33, because that's where I started, okay, and 2.25. So for this one here, we're looking at 27 as our position. And our final time is 3.5. So we're looking at negative 6 divided by 1.25, which should give us our negative 4.8 kilometers per hour. Is it also the same process for the entire trip? Yeah, it is. Okay. My initial position is 0. My final position is 27, and that takes 3.5 hours. So all I have to do is go average velocity equals total displacement, positive 27 kilometers divided by total time, 3.5 hours. Okay, and I should get 7.7 kilometers per hour. Positive 7.7 kilometers. How important is the positive? Very important. Okay? It did ask for a vector quantity. It didn't give me any directions like north or right or up. So I just have to write a mathematical direction. Positive. Okay? The slope is positive.
It isn't assumed if there's no symbol it's positive.
It is assumed
Okay.
if there's no other direction. Most of the time on a graph, they'll say kilometers north or kilometers west on the axis, so you'll know, okay, it's moving west or right or something. If it doesn't, then you go by anything above the x-axis is positive, and anything below the x-axis is
But
negative.
in our answer, if we just go like 7.8, you assume that's
Oh,
the
no,
closest.
I would want you to write the positive. Sorry, we make the assumption looking at the graph if it has nothing,
Yeah.
but our answer does need to have. Yeah, good question. All right, everybody okay with what went on there? Okay, that I put on like a quiz or a unit exam last year for Science 10. Okay, so if you were in my Science 10 class, you've probably seen that one before. All right, now, let's take a 5-minute break, okay? And we're gonna come back and talk about velocity versus time graph. So if you gotta use the bathroom, get a drink, whatever, okay, be back here at 1:11. All ones in a row, okay? Back here then. Okay, let's get back to this here. So we'll look at now velocity versus time graphs, okay? So velocity versus time graphs show us slightly different data. Right? Rather than showing us where an object is at various points in time, it's telling us how fast and in what direction the object is going at various points in time instead. So a position versus time graph and a velocity versus time graph of the same data can look very different. Okay, or of the same trip, I should say, might look very different. And that's what we're looking at here. These two graphs are showing us exactly the same trip. The one on the left is the position versus time data for that trip, and the one on the right is the velocity versus time graph for that data. Okay? Here's why that should make sense when we look at them. A position versus time graph that has a diagonal line says the object is traveling at a constant velocity. The graph on the right is showing that. But our instinct when we look at the graph on the right is that object stopped because the line is, it's horizontal. But remember, the graph on the right is telling us how fast and in what direction the object is going. It is showing us something whose velocity is constant and positive. Its velocity isn't changing, but it is moving in a forward direction. Okay? So it can be misleading. You always have to look at the title of the graph or the axes of the graph so you know which one you're looking at. Otherwise, it's easy to make a mistake and say, oh, that object stopped, when in fact, no, that object is not stopped. It is moving at 260 meters per second, which is definitely not stopped. Okay? That's really, really fast. All right, so how do I know it's moving at 260 meters per second? I mean, if I look at that velocity versus time graph, I'm kind of estimating, right? Like I can see the line for 250 and the line is slightly above that, so I'm saying 260. Is there a way for me to calculate it using the other graph? How do I calculate velocity from a position time graph again? Not distance, but displacement over time. Okay, so if I do that on this graph, okay, essentially then I'm going final position minus initial position over time. That's going to be 1,400 meters minus 100 meters over 5 minus 0, so 5, okay? And guys, this also translates to this, y minus b over x. I'm essentially calculating the slope of this line. So that's 1,300 over 5, which is 260 meters per second in a positive direction, which is exactly where that line lands on the velocity versus time graph. Okay, so according to this graph and the calculation I just made, my total displacement on this trip is how many meters? What's my total displacement? Nope. Okay, so this is final position minus initial position. My final position was 1,400, my initial position was 100, my total displacement was 1,300 meters, positive 1,300 meters. Okay, I started at a position of 100, I went to a position of 1,400. Okay, now, can I calculate that from this graph? You may have memorized this in Science 10. You calculate the displacement on a velocity versus time graph by calculating the area under the line. Does that sound familiar? Okay, I don't want you to memorize that. If it doesn't sound familiar, good, then you didn't memorize it, and I don't have to fix anything. Okay? Now, this graph is showing me velocity and time. So if I want to calculate displacement from velocity and time, I would take the average velocity and multiply it by time. Agreed? All I'm doing is manipulating v equals d over t here. Is everyone okay with me doing that? It's traveling at a constant velocity anyway. Right? So if I do that, take my average velocity, which is 260 because the line's flat, and I multiply it by time, which is 5 seconds, well, that comes out to 1,300 meters. Which makes sense because they did the opposite calculation on the other graph. Everybody all right with that? Okay. Now, did that calculate the area underneath the line?
Yes.
It did. It went base times height, right? Base was the time, the height was the velocity. Average velocity times time, and that worked. It was fine. Okay? I just don't want you to memorize it. It's the area under the line. I want you to understand from a formula perspective why that works. Now, that's fairly straightforward because it's a horizontal line. The velocity is not changing. But let's say I have that line instead. Now what's the object doing? It's accelerating. Okay? I've got a diagonal line that shows that the velocity of the object is increasing over time. That's the definition of acceleration. Any change in velocity over time is acceleration. Okay. From Science 10, anybody remember how we calculate acceleration? It's okay if you don't remember. I'm not all that offended. Just a little. Does that formula look at all familiar?
Yes.
Does it look like the one we were just using for the other graph?
Yes.
It sets up pretty much the same way. I mean, it's got different stuff in it, but the shape of it is the same. Why is the shape of it the same? Because it's going to calculate the same thing, the slope of the line. It's just on this graph, the slope of the line doesn't represent velocity. It represents acceleration. Okay? Slope always represents the rate of change of whatever's on the y-axis as a function of what's on the x-axis. So on this graph, it's telling us the rate at which velocity changes as a function of time. That's acceleration. On the other graph, it told us the rate of change of position over time, which is velocity. Okay? So slope always tells you that. Whatever's on your graph, the slope is telling you how quickly it's changing, or if it's flat, not changing. All right, so what's the acceleration of this line? Okay, all I gotta do is plug in my numbers. Final velocity would be, well, these go up by 50, so 450, 500, 550, minus 100, and that takes 7.5 seconds. Alright, so we got 450 over 7.5 seconds. So, sorry, this is meters per second divided by seconds. Sorry, I can't do that one in my head, okay? All right, so 60 what? Meters per second squared, or meters per second per second. Okay, how many meters per second it changes by? Every second, which we abbreviate meters per second squared because from a mathematical perspective, okay, if I'm doing this, right, meters per second divided by seconds, okay, sorry, by seconds, I wrote that wrong, got ahead of myself. By seconds, it's the same as saying meters per second times 1 over seconds, because you reciprocate and multiply, meters per second squared. Okay? All right. What's the displacement of the object with the slanted line? No? No, not yet. Yeah, we got to calculate it. Okay. I wasn't expecting anybody to just have it off the top of their head. All right, so we said you can calculate displacement from this graph by taking average velocity and multiplying by time. That's fine when the average velocity is a constant number. But in this case, velocity is changing. So that number doesn't work. Okay? Or that idea doesn't work necessarily. It can still work, however, as long as this is a straight line. Because then the rate at which the velocity is changing is uniform. So how do I calculate the area of a triangle? We're going back to what we learned in Science 10.
Base times height divided by 2.
Base times height divided by 2. All right. Since this line goes up at a constant rate, half the height would be right here smack in the middle. Well, that's my average velocity. Because half the time I'm going slower than that number, and half the time I'm going faster than that number, so right smack in the middle is my average. Height divided by 2 will be my average velocity. Right? And I divide that by the time, or sorry, multiply that by the time, and I've got base times height over 2. Okay? Height over 2 represents this part. Okay? The base represents that part. Another way to look at this. We're going to have this formula here in just a couple of days. D equals VI times T plus 1/2 AT squared. This calculates the area under the line as well. And I'm going to show you how it's just a little bit different. Okay. So for this line here, okay, we're going to take base times height, divide by 2, right, and we're going to get that area. So the height was, we said, 450, okay, because it starts at 100, and divide that by, multiply that by 7.5. So 450 divided by 2. And then multiply that by 7.5. Right. So that's how far that object will go. 1,687.5 meters. Okay. The average velocity is 225 meters per second. It accelerates from 100 to 550. So there's your middle point. All right. Well, let's say that the line doesn't start here at 100, but starts at 200 and goes to 400. All right, now how do I calculate the area underneath the line? It's not a triangle anymore. Now it's triangle and, yeah, separated into 2 different shapes. But now we're still going back to that whole science saying area represents area. Okay, we don't want to do that. Okay, that's memorizing. We don't want to do that. Okay, but what we are looking at is essentially 2 different parts of the trip. There's this part of the trip that's a rectangle, and there's this part of the trip that's a triangle. Essentially, this rectangle represents how far we would go if we continue to travel at the initial velocity of 200 meters per second. If we add that to how far we travel as a result of going faster and faster, we'll get the total displacement. Okay? That's where this formula comes in. Okay? This formula here calculates the area under the line on the velocity versus time graph. Initial velocity times time. This is my initial velocity. This is my time. That's base times height. It calculates that rectangle. Okay? This 1/2 AT squared calculates the area of the triangle. Okay? It takes the acceleration, cuts it in half, and multiplies it by the time squared, which is the same as going base times height over 2, okay, for that triangle. And it adds them together. Calculates the area under the line. Right, so that stuff's a little bit new. You guys haven't seen this formula yet. And I'm going to go over it in more detail when we go over acceleration. I just wanted to point it out for today. I'll go over that exact concept again when I go over acceleration. It'll probably make a little more sense then. All right. This is a graph of somebody running a race. Okay. It's a velocity versus time graph of somebody running a race. What is going on between 0 and 5 seconds? Yeah, the person is accelerating. Okay? Now there's a little curve at the beginning. Now that means that the acceleration isn't uniform at the beginning. After that it becomes like a diagonal line, but it starts out with a little bit of a curve. In a real sprinting race, that's actually what happens. When you first come out of the blocks, Okay, in a sprinting race, your acceleration is exponential and very non-uniform. Okay, because you've got things like a bit of slippage, regaining balance, things like that. And then once you get into the phase of the race where you're kind of becoming more and more upright, your acceleration becomes much more linear. Right? Especially if you've ever watched, I know he doesn't run anymore, but watch Usain Bolt. Okay, because he had the slow, for a guy who was so fast, his acceleration was ridiculously slow. Okay, and that's because he was really tall and skinny for a sprinter. Okay? Andre DeGrasse, that guy is like the least typical sprinter build you've ever seen. He's skinny and short, okay? Which is not a good combination for sprinters usually, but he's like the exception that proves the rule. Okay, there's usually two types of sprinters: the like hulking mass of muscle that's shorter, and the tall skinny guys. Okay, and Usain Bolt was the tall skinny guy. Donovan Bailey, who's a great Canadian sprinter, tall skinny guy. Okay, they typically have poor acceleration but incredible top speed. That was Usain Bolt's strength. Okay, if you ever watched him race, he was always like the last guy out of the blocks. He was like 6 or 7 meters behind everybody else, and then he would just reel them in. Okay, you could tell everybody else was like, "Where is he?" And they didn't want to look over their shoulder because they knew he'd be coming. Okay, especially in the 200 meter, because it was so fast. Like we're talking 17, 18 meters per second at top speed. Okay, that basically means he covers the distance from this wall to the other side of the chem lab. But when you're covering half the length of this room in one stride because you're 6'8", okay, you cover a lot of ground. Poor little Andre DeGrasse, he's got short legs. He doesn't cover that much space. I don't know if you guys have seen, they had on Instagram like all summer, all of the old races when DeGrasse was kind of younger and Usain was, the veteran racer, and Bolt would just toy with him. It was funny. Look over, oh, you're coming? And he'd just speed up. It was effortless. DeGrasse is just going as hard as he could, and there's nothing he could do. Okay? So, first part of the race, we've got acceleration going on. What's going on here? Constant velocity. Okay? In a typical sprinting race, especially in the 100 meter, they just go as hard as possible, and they hit this point where no matter how hard they pull, they can't go any faster. They hit their maximum speed, and then it's just a matter of maintaining that maximum speed for as long as possible. Okay? And then, this would be the point where they what? Cross the finish line, yeah, and then they slow to a stop. Okay, we go back down to 0. Okay, so that's what we're seeing there. Okay, so I might ask you, I might give you a graph and just ask you, interpret this graph. Don't ask you to calculate anything from it, just say, what's happening in this graph? Well, first the object is accelerating, then it's traveling at a constant speed, and then it slows to a stop. Okay, something like that. All right, so this is not something you have to necessarily write down, it's in your notes package. Okay, but if we're looking at interpreting that graph, the vertical value of any point is how fast the object's going at that point in time. Okay, and the area under the line, which again we don't want to memorize or anything, okay, but that's going to represent our displacement. It's average velocity times time. All right, so we'll look at a few examples here and then we'll call it good. So I want you guys to try this one, or this part here. Okay, so you got that velocity versus time graph. This is also on that same, it's at the top of page 5 in your digital workbook if you want to be able to blow it up bigger. Okay, so we want you to be able to calculate here the average velocity, which is not something we talked about. Okay, actually, you know what? I don't want you to calculate average velocity. On this one, I want you to calculate total displacement over the whole trip and average acceleration over the whole trip. Okay, so average acceleration and total displacement. And remember, I did give you your formula sheets here, but just so you have them, okay, just so you have it. Average acceleration, okay, is calculated that way. Give you a few minutes on that. All right, let's have a look at this one here. So, we've got, for the first part of this trip, okay, that'll be the first 20 seconds, the object is accelerating. Its velocity is changing from 0 to 40 meters per second. Then it travels at a constant velocity of 40 meters per second for the next 30 seconds, and then it accelerates from 40 to 80 meters per second over the final 10 seconds. So if I want to calculate the total displacement, I need to break it up into each section of the graph, which is kind of like what we learned how to do in Science 10. Okay, I'll have this part here, okay, which goes to here, but I'm actually going to extend out, and then I'll also have this little piece here. So I'll have these kind of three pieces that I've got to deal with. Right? So for the first part, I'm going to calculate the total displacement here by simply taking average velocity and multiplying by time. And the average velocity is halfway between 0 and 40, which happens to be 20. In other words, base times height over 2. Okay, so I'm going to take my 20 meters per second and multiply that by 20 seconds. Okay, so 20 times 20, okay, is 400 meters. Okay, in that first part. Then I've got this whole section here, and I know there's no line here where I drew the dotted line, but because the object accelerates after 50 seconds, I still have to consider how far it would have gone had it maintained this velocity and added on to that extra bit it covers because it accelerates. Okay? Again, I'm going to take average velocity times time. That's 40 times 40. Okay? This is going to give me what? 1600, right? Okay, and then I've got this little bit here. The average velocity goes from 40 to 80, so the average velocity will be 60, okay, times 10, right? So, sorry, yeah. Actually, I just want to do this section here. So the height of this one is from 40 to 80, so the height is 40, okay? Divided by 2 is 20, okay, times 1. So this is another 200 meters here, okay? Everybody with me on that? Okay, so now what do I do with those three numbers? Add them together. Okay, so I've got 2,200 meters, right? Positive 2,200 meters. All right. Could I calculate the average velocity now? I just calculated total displacement, right? I know the total time is 60 seconds. I could calculate the average velocity over the whole trip now if they wanted me to, right? But the other thing we were asked to do is to calculate the average acceleration over the whole trip. Well, average acceleration is final velocity, which is 80, minus initial velocity, which is 0, divided by total time, which is 60. So that should be, we're looking at 1.3. So the average acceleration over the whole trip, it doesn't mean it accelerates over the whole trip, but on average, over the whole trip, its velocity changed by 1.3 meters per second per second. All right, so hopefully that's ringing a little bit of a bell for everybody. We're going to spend some time on this, so don't panic. It's not like I'm going to teach you this and then just move on to something else tomorrow. Oh, by the way, we're moving on to something else tomorrow, but we're going to come back to this and keep doing some more of it yet. Okay? Speaking of what we're moving on to tomorrow, because we're going to be doing a graphing lab, I think it's tomorrow or Thursday, I don't remember now. Okay, I need everybody to download this app on their phone. It's free. It's called Spark View. Okay, that app will allow your phone to communicate via Bluetooth to our data carts. Okay. When you're in Science 10, you know, had the carts on the floor and the measuring tape on the floor, and you had to like do it. You had to measure that sucks. We only do that because you're in Science 10 and we want to make you work. Okay. In Physics 20, we have these special carts that record all of that data for you 20 times per second. Okay. They give you an incredible set of data points from which to work. You can plug that data directly into Google Sheets without having to manually enter it, okay, and it makes these wonderful graphs for you. But you need that app in order to be able to collect that data from the carts. Okay? Only one member of your group will actually do it, but we don't know who your groups are going to be yet, so everybody can get that on their phone, we'll need it a couple of times throughout the course. 4 times throughout the course. Okay. All right, so if you can get that on your phone, that would be awesome, and we'll leave it there for today. You will have a quiz on Thursday, okay? I'll post it tomorrow, and it will probably be on a little bit of vehicle geography and some graphics.